we're going to show you the many uses of a variable. First of all, we could have some number plus 3 equals 7. In this case, we're going to let n be an unknown quantity. So we could have n plus 3 is 7. So we don't exactly know what n is until we solve that equation. So n stands for an unknown quantity. Here, if we subtract 3 from both sides of that equation, we'll find that n is equal to 4. So there's one use of a variable. Now, a second use of a variable. If we have a problem like 7 chairs cost $350, in this case, we're going to let the variable, we'll call it C, stand for the cost of a chair. So this is a value that can change. Here we have 7 times the cost of a chair is $350. So if we divide each side by 7, we find that the cost of one chair is $50. Another way of thinking about variables. Another way to think about variables is a variable can represent how many something is. So for instance, we have a problem where we let k equal or represent or stand for the number of nickels that we have. Now, in that case, if k stood for the number of nickels we had, then 5 times k stands for the value of the nickels that we have. So if we had, say, 7 nickels, if k was 7, then 5 times 7, we'd have 35 cents. Now, one of the other things we can do is just to simply let the variable represent an object. So here, for instance, we'll let n stand for an apple. So if we have n plus n, well, that's 2n, because apple plus apple is 2 apples. Now, if you have addition or subtraction problems using variables, then the best way to think about it is to let the variable stand for an object, because we can add and subtract objects together. So, but we prove it using numbers. So we think about it using objects, and we prove it with numbers. So say, for instance, we let n be 5. We don't know what it is, but say it's 5. So 5 plus 5 is 2 times 5. Well, 10 is the same as 10, so we proved it using numbers. So we think about it using objects if we're adding or subtracting expressions, and we prove it with numbers. Now, here's a couple of examples that we have. If we have x plus x, well, we can think about this as objects. So x could stand for an apple. So an apple plus an apple is 2 apples. And then we prove it with numbers. So say, we just pick a convenient number. Something like 5 usually works pretty well. So let x equal 5 and see what happens here. We have 5 plus 5 equals 2 times 5. Now, if that's true, then we probably know that we added x plus x together correctly when we got 2x. So 10 is equal to 10, so we know we did it correctly. Now, let's try another example. Here's another addition example using variables. It's best to think about this, I think, using objects. So if x again stood for an apple plus 3 apples is 4 apples. So we think about it using objects. Then we prove it using numbers. So again, if x is 5, we have 5 plus 3 times 5 equals 4 times 5. Now you can see why thinking about it with objects is a little easier than thinking about it with numbers. Because with numbers, now I can prove it pretty easily, right? 5 plus 15 is indeed 20. So I added x and 3x together correctly to get the 4x. Now here's another example. This is just like the examples we did with if you have multiplying exponential expressions and the base is the same. keep the base and add the exponents. So when we're thinking about multiplying and dividing exponential expressions, it's best just to think about them as numbers completely. Think about it as numbers and prove it with numbers. So here, this is the first product law of exponents. So we have 2 times, keep the base, and add the exponents, because s times s times s is s cubed. Now we want to prove that. So let s equal something like 5 again, and we have 2 times 5 times 5 times 5 equals 2 times 5 cubed. Now, 5 times 5 times 5 is 125, times 2 is 250. 5 cubed is 125. 2 times 125 is 250. So we again proved that our work is true, but we thought about it using numbers, and we proved it using numbers. Now here's another example, multiplication example. We think about it as numbers. A number times a number times a number. So we have 5. This is m times m. We're multiplying exponential expressions. We keep the base and add the exponents. Again, we can just prove that that's true. Say we let m equal 3. Try to pick a number that doesn't appear anywhere up there. So we have 3 times 5 times 3 equals 5 times 3 squared. Well, 3 5s are 15 times 3 is 45. 3 squared is 9. 5 times 9 is 45. So we proved that example also, thinking about it using numbers. And here's another one, the same exact problem, different letters. So we're going, these are the exponents, we multiply. P times P times P is P to the 3rd power. And again, you want to try a number like 5 in there, something that doesn't appear up there. So we say let P equal 5. We'd have 2 times 5 times 5 times 5 equals 2 times 5 cubed. Well, we'll see if this is actually true. 5 times 5 times 5 is 125. 2 times 125 is 250. This problem look familiar? 5 cubed is 125. 2 times 125 is 250. So we've checked our work. And then finally, the last problem. Now these are a little mixed up, but we like to put the letters in order that they come in the alphabet, put the number first. So here's the 7 comes first, then x times x is x squared, and then the y. So we can prove this is true also. So we say, pick numbers that aren't there. So let x equals, say, 3, and y equals, say, 4. So we have 3 times 3 times 4 times 7 equals 7 times 3 squared times 4. So now, let's see if that's actually true, right? So 3 times 3 is 9, 9 times 4 is 36. And let's see, we have 7 times 3 squared is 9 times 4 is 36. So 36 times 7 equals 7 times 36. Of course, it's the same thing. 7 times 6 is 42. 7 3 is 21, and 4 is 25. So 252 equals 252. And now we should be in really good shape to be able to do the problems that are in the book with adding, subtracting, multiplying, dividing, exponents, exponential expressions, and variable expressions. Happy computing.